Let's talk about bases and dimension. A basis is just a set of linearly independent vectors that span an entire subspace or vector space, whereas the dimension of a vector space or any space is just the number of vectors that are in any basis for that space. So an example is for R2, a basis, we could write it as the vectors 1, 0 and 0, 1. And simply because these two vectors, we know they're linearly independent and they span all of R2. They're just like the x and y axis. And notice that there are two vectors in the basis. So we say the dimension of this vector space is 2. And the math way of writing that is with the word dim. Okay. By the way, there's an infinite number of possible bases, that's the plural of bases, for a vector space. And that's because as long as you pick any two linearly independent vectors, it works, right? You can span any other vector in that space. Can you think of other possible bases? And in general, to span any vector space, Rn, you always need n linearly independent Rn vectors. There is something called a standard basis in Rn, and it's basically made up of the column vectors of the identity matrix. So the basis that we saw before for R2, that is actually the standard basis. And there's this notation that people use with it is the letter E. So if you ever see that, it is referring to the standard basis vectors. Notice again the dimension is 2. For R3, the standard basis vectors would be these. Again, notice we use this E notation, and the dimension would be 3. How do you find any other basis for R3 that is not the standard basis? Well, you start by choosing any two linearly independent vectors that you like. So if we make it easy, we can choose something like 1, 2, 3 for one vector and 4, 5, 6 for the other one. Notice they are linearly independent because they are not multiples of each other. So now it's a matter of coming up with the third vector and making sure that it's linearly independent. So we play this kind of algebraic trick. We add them, but if we add them, the result is actually linearly dependent. So the way to make it independent is you tweak one number. So like this 5, for example, you could make it to a 4. And basically that ensures that the three vectors are now linearly independent. So together they create a basis. And if you wanted to prove that they're linearly independent, remember you could put them in a matrix and row reduce, and you would notice that you get a pivot in every column. Okay, what about finding a basis for like a subspace of R4? Let's say that they define the subspace with an equation such as this one. So we notice that there are 4 variables, but just one equation. And so because of that, 3 of these variables are free variables. Now, the nice thing is it really doesn't matter which ones you called free variables. Choose any one that you like, and we're going to solve for it. And what's going to happen is when we solve for one of the variables in terms of the 3 variables, that will give us 3 vectors in our subspace. So when I look at this equation, I'm thinking if I put the negative x4 on the right side, it will become like positive x4, and it just makes it easy to solve for x4. So that's what I'm going to do. I'll solve for x4. That means that x1, x2, and x3 are going to be my free variables. So remember, we are coming up with a basis for vectors in R4. Vectors in R4 have 4 things, right? And so those four things are our variables, x1 through x4. But remember that we said that we only have 3 free variables. So we're going to rewrite x4 in terms of x1, 2, and 3, in terms of the free variables. And from here on out, it's just plain algebraic tricks. You want to rewrite these vectors sort of like when you did those span problems and you wrote out the solution as the span of 3 vectors. Guess what? It's exactly the same thing. In fact, you were coming up with a basis all along. And so those 3 vectors that we get, those are the bases. And notice that because there are 3 vectors in this basis, the dimension of the subspace is actually 3. Okay, what about vector spaces that are made up of polynomials? Do they have a basis? And if so, what do they look like? It's exactly the same thing. A basis, it's always made up of linearly independent vectors that span the space. However, the vectors right now are actually polynomials. So the standard basis for a polynomial space n is something like this. You start out with number 1, and then x squared, x cubed, and so on until you reach the last degree of that polynomial. So for example, let's say the vector space P3. This is actually all polynomials with degree less than 3. Okay, so it's not a cubic, it's actually a quadratic polynomial. The reason for that will become obvious as we look at the basis. So the standard basis for this has 3 objects, 3 vectors. The first one is 1, then x, and x squared. They are 3 linearly independent vectors, and any linear combination of those 3 vectors, with those linear combinations, you can make this other one up here, the main polynomial. So you see why it's P3 is actually referring to polynomials with degree less than 3 because there are 3 things in the basis. So let's find a basis for a subspace of P3. Let's say we have this crazy thing here where it says find a basis P of x, Q of x for the subspace of all set of functions in the vector space P3 such that if we take the derivative of these functions at x equals 4 and they should equal the polynomial at x equals 1. Okay, wow, how do we even start this thing? Well, the first thing is to write out what the standard polynomial in P3 looks like. So as we saw before, that's just a quadratic. So we're going to go ax squared plus bx plus c. Then you have to apply the given conditions. We were told that if we take the derivative and plug in x equals 4, it should equal the polynomial at x equals 1. So we take the derivative and we plug in x equals 1 for the polynomial, set them equal to each other, and what happens is you notice that b cancels out, and then we just kind of rearrange it, and we see that c equals 7a. So this is going to be key, because with that, we're going to rewrite the polynomial, but instead of c, we're going to write 7a. And so that's exactly what we do. And this result, we're now going to rearrange as a linear combination of 2 polynomials. How do I know it's 2 polynomials? Because there are 2 different parameters, a and b. And yeah, sure, they told me in the problem that I have to find the basis of 2 polynomials, but if they hadn't told us that, we would know because we have 2 parameters, a and b. Okay, so just rewrite it, group all the stuff that has a, group all the stuff that has b, and whatever's attached to those are your 2 polynomials that make up the basis. Okay, so polynomial x squared plus 7 and polynomial x, those two polynomials are the vectors in the basis of this subspace. So because there are two of them, we say the dimension equals 2. Now, with a problem like that, how do you even know if the answer is correct? Well, remember that a basis is basically the necessary vectors that you need to span anything in that space. So if you take any linear combination of those vectors, then the requirement that f prime of 4 equals f of 1 should still work, right? So that's exactly what we're going to do. Let's say we take 100 of the first polynomial and negative pi of the second polynomial. So when we try that, we get this, right? And we plug in f of 1, we would get 800 minus pi. Now we're going to take the derivative and plug in 4. And look at that, we get exactly the same result. So as required, f prime of 4 equals f of 1. And so that's how you could figure out if your answer is on the right path. Okay, so the last thing we want to do is get to matrices. What about vector spaces that are made up of matrices? How do you span those things? And can you figure out a basis for it? So just as before, we have a standard basis, and it's basically all these 1, 0, 0, 0, 1, 0, and so on. Notice that there are 4 things in this basis, and that happens to be 2 times 2, which is the dimension of each matrix. So these 4 linearly independent vectors, they make up a dimension of 4. Now, it's kind of weird to think of matrices as vectors. So if that's really bothering you, just instead of calling things vectors, call them objects. It's totally cool. Okay, so let's find the basis for a subspace of m by 2 by 2 matrices. So here we have, we're supposed to find the basis for the subspace of all matrices that are 2 by 2 such that their trace is 0. Okay, so as we saw with the polynomials, or with any vector really, you just want to write out the standard form of the first of the vector space, and you apply the given condition. Okay, so make up some matrix A, B, C, D, 2 by 2, and the trace happens to be the sum of the diagonal entries. Okay, so the requirement is that the trace has to be 0. So algebraically, that tells us that D must be negative A. And so as before, you rewrite this object with that requirement. So instead of this cell D, we're going to write negative A. And the key thing now is to rearrange it as a linear combination of 3 matrices. How do I know it's 3 matrices? Because how many different parameters do we see? A, B, and C, we see 3. Okay, so we just factor out A, B, C, and we write 3 matrices with each of those factors. And that's it. Those matrices make up the basis for this subspace. Because there are 3 matrices in the basis, we say the dimension of this subspace is 3. If you have any questions, don't forget to post them on the discussion board.